of functions that give rise effectively to positive semi-definite matrices and various other conditions, but that's the most important. So many things can be a kernel. The simplest is simple vector dot product. So here we've got a set of images, just simple geometric objects. We're vectorizing those and just dot producting them. Obviously the dot product of something with itself is 1. Everything else has some set of relationships to each other. So the idea with kernel learning is you're doing learning with this entity, the kernel matrix, rather than with the set of training vectors and their labels. So providing you can kernelize your data and get it into a matrix form, you can use that in any classifier. Importantly, it can be used in any classifier that has a gram matrix, vector of inner products. So in fact, this wouldn't be much use in practice because you'll already be dealing with because this effectively is a gram matrix, the vector dot product. And in fact, this wouldn't work at all well in practice for a genuine image recognition problem, because vectorizing an image by unwrapping it is going to be enormously prone to any kind of offset variation, scale variation, and it would fall over hopelessly in a real setting, but you can hypothetically think about it. So almost always you're using a more complex kernel function than a vector dot product. But what you can always show is that provided your kernel obeys Mercer's condition, you can show that it is equivalent to a vector product in some Hilbert space. Now, you don't know what that Hilbert space is or its dimensionality necessarily, but you know that it exists. So basically what this means is if you're using a support vector machine, you're building your linear decision boundary in this Hilbert embedding space, which is correlated with perhaps something much more complex in the input space. In the DNA example, you don't have an input space at all. So you can't make this comparison. This is the only space that exists. So basically, you've got this feature map phi that is excellent. That's all you know about it. You can, if you really want to, go and pull it out retrospectively. But the nice thing is you don't have to care. So you've induced this embedding. And this, therefore, beefs up the power of certain classifiers and regressors enormously. Wherever you've got a gram matrix, wherever your training data is representable as a gram matrix, you can chuck that gram matrix away and replace it with an arbitrary kernel function. So it's very modular. You can slot stuff in. And this effectively increases the power of any regressor or classifier enormously, gives a huge range of options. But again, you've still got these nice characteristics like, just defining your decision boundary in terms of support objects with all that implies. And you can kernelize deep learning if you really feel that you've got to use a deep learner. So that's the best of all possible worlds in principle if you've got loads of data. So just to bring it all to a conclusion, basically there aren't many places that machine learning isn't going these days. It's starting to be used where people would do statistical analysis. It's obviously not completely supplanted statistical analysis where you need risk assessment, but then there are fully Bayesian approaches to machine learning where you can pull out exact risks and so on. But basically, there are going to be loads of different applications in one or other of these areas: pattern mining, pattern recognition, prediction. So there's obviously a lot of existing methodology. There's new methodology being generated all the time. But also, what we're finding is that new data domains really start to define new problems. It's like, who knew you need a recommender system until Amazon came along? It starts to define, so you can define these problems mathematically and come up with appropriate theories. So the application of data science to machine, or data to machine learning is win-win. One can simply take could solve many problems that were previously insoluble by applying machine learning to a new data domain, but equally that data domain is perhaps suggesting new ways of approaching the theory. So that's about it. That was an hour and a bit. So hopefully that was pitched it roughly the right.
Thank you. Maybe there are some few questions remaining.
Do you know how support vector machines scale with the size of the input?
Very, very badly indeed.
The size of features and or size of.
So you mean scale in terms of?
Yeah. So I mean, how long will it take to train?
So
I mean, if you had, I don't know.
So they're order n cubed. So the square of the cube of the number of entities you're training with. What's generally speaking?
And the features?
Well, this is another thing. If you're kernelizing, you've basically immediately turned a problem from being one of dimensionality to one that's the size of the objects. So that's another nice aspect. So it means, for instance, I do a lot of medical healthcare analytics, and you have a fixed population, and you can arbitrarily increase the number of features you chuck at the problem in terms of what kind of embedding Hilbert space you're going to get out of it. The dimensionality actually isn't affected by that. It's affected purely by the choice of kernel.
Okay.
So effectively, you're constrained by the number of training objects. It doesn't scale brilliantly. I mean, it's not, the best possible world would be linear or sublinear scaling, and it's order 3. So you can't shovel enormous.
If you have one. If it's n to the 3, if you have, and I don't know, of course, what's the worst case. Maybe it's probably worst case analysis, but I don't know how it behaves with whether.
Well, there certainly comes a point. I mean, if you're doing image classification.
I mean, if you have 1 million objects, if it's really n over 3, you never finish.
Yeah, exactly. So there comes a point, and this again, where training data, for instance, for deep learning is precisely what you want because.
I see.
So, if you've got 1 million images to classify, you wouldn't use a support vector machine. I mean, that's the point at which. I mean, there are ways of mitigating it. You can, a whole range of strategies for improving the scaling of support vector machines. But if someone handed me a bunch of 1 million images, I'd go to CNN. It's the first port of call. Especially now there's a fairly well-established pipeline for doing that.
In your problem, are the boundaries always connected?
The decision
boundary
connected to.
I mean, they're actually one single boundary rather than different components. I can imagine problems where you've got a cluster in one area and a cluster in another, and you kind of
absolutely. Well, but that's a multi-class problem. So
just similar to.
I mean, for instance, in this ensemble decision, the sum over several decision boundaries has created just a new decision boundary.
Okay.
But if you're dealing with multiple classes, then clearly it's not going to be a single hyperplane or an n-dimensional or single n-1 dimensional hypersurface. You're going to get intersecting. There are different, lots of different strategies for creating multi-class classifiers from binary classes. So
support vector machines can actually.
Oh yeah, you can definitely. So I mean,
multi-class.
Yeah, I mean, the simplest, it's certainly not the most effective. It's just to do one versus all classifier for each. Okay. I mean, that would be very bad in practice because you have massive class imbalance. So they're far more effective strategies like error correcting output codes. But you definitely can. It's not as natural maybe as it is in a deep learner where you can just add another neuron and get a new class. But it's only one extra problem on top, and typically that's not even a learning problem. You can actually treat it as a learning problem in its own right, though.
So
Did you mentioned prediction, recognition, and what else is it? There's 3 domains.
Prediction, recognition, and was it data mining, something like that? Pattern mining, yeah.
So is control? I thought control problems also now basically in the domain of machine learning as well.
Yeah, actually, yes. Well, there's the whole kind of world of reinforcement learning. Is that a mixture of? Well, arguably it's prediction, but with a with a control output. But yeah, reinforcement learning.
Online learning is kind of like sort of not training and then performing, but actually training as performing.
Yeah, so online learning I would say is maybe a combination of prediction and recognition, a bit of both. But yeah, actually, in terms of outputs, certainly I think reinforcement learning could arguably be given a separate circle of its own, although clearly it's in the business of prediction and so on. So this is where you're trying to optimize a strategy with respect to a long-term horizon of outcomes. But human-computer interfacing, obviously tends to have to be adaptive. The system has to adapt. So online learning, adaptation in general is a whole area of its own right. And typically, you can treat, in machine learning terms, the problem of online learning is one of saying, I've got a new data point, how do I incorporate that into my classifier without having to retrain on my entire set of data, which falls over. So there you want a classifier that you can update very easily. So there are approaches to that. There are other, even more open-ended forms of online learning where you can learn new classes, where a new class comes along, so you're doing some unsupervised learning, you determine that something is actually a new class in its own right, you give that a label, and then you can recognize it in the future. So that comes into a lot of reinforcement learning strategies.
So actually in the 60s in the Soviet Union there was a discussion between a few people, between Sitkin and Stratanovic basically, about whether learning as a science is a different field from Bayesian methods in general or not, and should they be actually separated. What separates learning from things like just Bayesian methods of estimation? And Stratanovic argued that learning is just the only characteristics